Okay, we're doing Lab 7. It's made up of 4 exercises or activities that are taken from Compadre Quizlets. Work and energy problems 6.2, 6.5, 6.6, and 6.8. At the end of the video, there will be a table of contents that will give you the time at which I began each Quizlet. Here is problem 1, Quizlet problem 6.2. So let's watch it. So the clock starts and nothing happens. The clock is running, nothing's happening. And then at 1 second it starts to fall, it appears to accelerate, it hits a nail, it drives the nail in and stops. So this is a lab exercise. We're here to observe carefully, to take measurements, and to use our knowledge of physics to answer questions and predict the outcome of events. So before we begin answering the questions, let's just review what we're seeing. We're seeing 3 parts. We're seeing a time from 0. We could check it out, but it goes to about 1 second. Nothing happens. So that's part 1. Really, the clock runs and nothing happens. Then at that time, the brick is released. At least it appeared in the video. We can take measurements to check to see if it actually falls and accelerates at 9.8 meters per second. But assuming it does, the brick falls, and at some time that we didn't pay attention to, it hits the nail, and then it begins to decelerate. So 3 parts. The first part where nothing happens, the second part where it's a free-falling object, and the third part when it touches the nail and drives the nail in and comes to a stop at the bottom. And in this case, we have the stepping button, so we can step back. Oh, it's not stepping back. Oh, there it is. There's a little delay. And so at 1.45, it hasn't hit. 1.46, it hasn't hit. 1.47, it hasn't hit. And 1.48, it hits. But you got to be careful. Did it hit exactly 1.48, or did it hit somewhere between 1.47 and 1.48? We don't really know that. That's part of the lab. That's the part of this exercise that makes it a lab. You've got to observe carefully and not make any assumptions. We want to get good, precise measurements. So we want to learn from this too, right? So what happens? In the beginning, nothing happens. In the second part, where it's a free-falling object, what's happening? From an energy point of view, the brick is falling. It loses potential energy, and it gains kinetic energy. And so potential is changing into kinetic, and no work is being done. But once it hits the nail, it has kinetic energy that then all goes away. The entire amount of kinetic energy as it touches the nail is lost, right? It stops at the end, and all that energy is put into the work done to compress the nail. And at this point you should know, and if you don't, when work is done, energy doesn't disappear. It means that energy, the kinetic energy of the brick, is transferred through work to some other place. And you can imagine where it is. In this case, it's going to be heat. Mostly the heat in the nail, or in the energy it took to deform the wood to drive the nail in. So this is good practice, right? I'm taking a long time talking. You're probably getting bored, but it's important that you look and observe and see the different parts and think carefully through the energy and any energy transformations that take place in each part. Okay, now we're ready to do the problem, answer the questions. So another part that's not immediately obvious and often leads to confusion is that there are 3 relevant distances here. So the first one is the distance that the brick travels when it's in free fall. So that's from the bottom of the brick to the top of the nail. Then there's the distance that it compresses the nail. And in this case we call that R, because we're going to use it to calculate work, where work is FR cosine theta. So you could give it whatever name you want, but in this case that's that distance. And then there's the total distance it travels, right? From the bottom of the brick all the way down to where it stops. And of course this is delta y for the free fall. This is delta y total. And then the part that compresses the brick. And in order to get those measurements, we have to use the cursor and measure the bottom of the brick, the top of the nail, and the bottom of the brick at the end of the problem where it stops entirely after it's compressed the nail. It won't run for me now because I expanded it. Okay. So the first part of the lab is taking measurements, and for that you need the cursor, which I don't have. It doesn't work on the iPad, so it's a cross piece, and you want to put the very, very center of that cross, the cursor cross, right at the very center of the nail to get the position of the top of the nail. And you want to do the same thing at the bottom of the brick, and that will give you the distance it falls. And then when the brick hits the nail and drives the nail in, then you put your cursor at the very center of the bottom of the brick at the nail to get that position. And from the position here, the position here, and the final position, you'll get those 3 distances that I mentioned previously. And from those, you do the calculation. So the energy from the top to the very end is the delta y, or the h, that gives us our delta PE, right? Because delta PE equals mg delta y, or mgh. And that's the full potential energy. And notice I'm not mentioning kinetic energy, because when the brick starts, it has no kinetic energy. And when it stops at the bottom, it has no kinetic energy. So all the energy is just change of potential energy. And so when we write the work equation, the potential energy term is 0. The change in potential energy is 0. And since the work is also the force times the displacement times the cosine of the angle, that in this case is the change in potential energy, we can get the force because we can measure the R. And that R is that distance over which this force, the force of the nail on the brick, happens. And of course it's a negative work because the displacement of the brick is down, whereas the force of the nail on the brick is up. So it's the cosine of 180 degrees, which is a -1. Makes sense. It's a negative work. Then there's the curiosity piece. And that curiosity is, it was my curiosity anyway, does the brick actually fall as it's supposed to? Does it have an acceleration of 9.8? Now that acceleration of 9.8 meters per second is only going to be true before it hits the nail. So we use our kinematics equation. It's in the lab. Delta y equals Vy initial t plus 1/2 AY t squared. You see how much we use these? This is equation number 3 from the equation sheet. And of course, the initial velocity of the brick is 0. So we do the algebra, and we get the acceleration in the y direction, which we expect to be 9.8, is going to be 2 delta y over t squared. Okay? And so that delta y is a different delta y. That delta y is from here to the top of the nail, because that's the time that it's in free fall. And that's a little bit less than the other delta y that we used in the previous part. And the time, remember, we said it was between 1.47 and 1.48. So if you use 1.48 seconds to do this, and you get a number that's a little bit too small, then it might mean that the time is actually somewhere between these two numbers, like 1.475. So that's the curiosity piece, to see if we actually get an acceleration which is 9.8 or close to 9.8. So exercise number 2, Bizlet problem 6.5. It's always a good idea to read the description carefully before you start. The mass of the block, identical blocks, a 10 Newton applied force, etc. Read it over, and then we want to watch the thing. So one block goes up, and one gets pushed to the right and then back to the left. So they all start and end in the same place. One moves along the vertical, the other moves along the horizontal. And this is an exercise in understanding the concept of work. So in the Moodle problem, you'll see a table where you're going to collect position and time data so that we can understand the motion of both of these. Like, how far do they travel? How long to travel that far? Are they moving at a constant velocity? Are they accelerating? We'll be able to use the data to answer all those questions. And then the second part is to understand what's going on in terms of work. And for that, let me write down the 2 work equations. So don't forget, what we're doing is we're trying to understand the concepts of work and energy and understand them in the context of many different examples. So the definition of work, actually what you should know is the definition of work in the general sense is an integral, because the force and the angle are not always constant. But in the simple cases we're studying, the work you do is the product of the force you apply, the distance, the displacement you push the thing or pull the thing, and the angle between those two vectors. That's the our definition of work. What is this equation? Looks familiar, right? This is the law of conservation of energy. This says that the kinetic energy and the potential energy, and just to remind you, K is short for KE, and U is an alternative, widely used term for PE. PE is potential energy. It's easy to understand. U, you have to learn it. That's what is often used in calculus-based physics textbooks and in engineering if you study thermodynamics and so on. So I used those symbols. So work changes the energy of a system. If the work on a system is 0, the energy can change from kinetic to potential, but the total energy will remain constant. That's the law of conservation of energy. So when you see this equation, you should see the definition of work. When you see this equation, you should see the relationship between work and changes in energy in a system. Remember, one of the descriptions of work is It's the process by which energy is transferred from one object to another or one place to another. So a person pushing a block is doing work, and how is it changing the energy? In this case, it's not changing the energy, right? The kinetic energy remains constant, the velocity is constant, it's not going up and down. So where is the work going? So in this case, the work is going into the work that you're adding to the system as you push it is being lost to friction. So there's no net work. So this is the applied force when it's going to the right, and this is the force of friction. And they're equal and opposite. And they have to be, right? We know that from Newton's second law. There has to be two forces that sum to zero because the object is not accelerating. That's from a force point of view. But from an energy point of view, the energy that you expend pushing the block back and forth does not go into a change in kinetic energy, does not go into a change in potential energy. It all goes into friction. It's kind of lost to heat of the two surfaces rubbing each other. So this is what we're practicing, trying to follow and track energy and work in a wide variety of situations. When you lift the block, on the other hand, you're doing, the block's going up, you're lifting up, you're doing a positive work, and you're changing the potential energy. There's no friction, right? And so when the block gets lifted to the highest point, the work you did went into changing the potential energy. When the block comes down, if you let go of it, it would accelerate and gain kinetic energy, but you're holding back. So now, as the block is going down, this is the tricky one. The force you're exerting is up, but the displacement is down. So that's a negative work. You are actually, although in the case of a human being, it doesn't work, you are actually receiving energy. That's a negative work. The block is giving you energy. And, well, in real life that doesn't work. But in order to understand it, think of the block wrapped around a wheel. And as the block falls, it turns the wheel, and the wheel turns a generator and generates electricity. So as the block falls at a constant speed, the energy of the loss of potential energy goes into producing electricity. So when you lift the block and then lower it back, you did a positive work going up and a negative work going down, and the net work that you did was zero. And the net change in kinetic energy and potential energy from going from the bottom to the top and back to the bottom is obviously zero, so the net work would have to be zero. So that's the energy analysis of everything in this problem. Good luck. Okay, number 3, problem 6.6. Take a minute and read the description carefully and highlight or underline what you think is important in the animation. It's going to be important to note. And then observe the thing and see what you see, and then in words describe the work and energy transformations that take place during the animation. So just do that as an exercise in learning, and then come back and listen to me. So here are the items that I would highlight. 2 kilograms, so we know the mass. The position values are going to be in meters if we measure distances, and time is in seconds. The units are important. No friction between the mass and the ball. And the mass slides. It does not roll. Okay, well, you wouldn't know what that means yet, but we'll learn that later. if the mass were rolling, there would be energy in the rolling, and we would have to account for that rolling or rotating kinetic energy, and we don't know about that yet. So even though it's a ball, think of it sliding and not spinning, and so the only kinetic energy is the one we're familiar with, the 1/2 mv squared. All right, let's play the thing. Let's see if it'll run for me. So it rolls up and back and up and back and up and back, and it stops, and the total time is recorded 11.2 seconds. So it did, what are we noticing? First thing I notice is it did 3 cycles, 3 complete cycles. And so when we get to find the velocity at the bottom, we're going to have to know the time it takes. And so if the cycles will divide into 4 equal parts. The ball will go down to the bottom from the top, and then it will reverse and go back here. But that's only a half a cycle. Then it will roll back to the bottom again, and then back to the top. So there are 4 parts to that cycle, and it does 3 cycles. That will be important. We also have this stepping function, right? So we can move the ball in small increments. But when you do this, if you measure very carefully, this is a lab, and you look at that position, it's not quite at the bottom. And then if I go to the next position, it's past the bottom. So it doesn't actually reach by 1 second, it's past the bottom. Whoops. And won't go backwards for me. But at the 0.9 seconds, it was not quite at the bottom. So sometimes we can't get the exact position of something by using the stepping function. And that will be the case in this exercise. So let's do the energy analysis together. This is the important part. This is the understanding part. This is the part you really want to just not get used to using equations to put numbers in and get results, but really understand the equations. So we have our 2 work equations, the definition of work. We discussed that. It's a result of a force, a displacement, and an angle. And the relationship between work and the change in energy of a system. This is the law of conservation of energy. And so what do we see in this case? We see there's no external agent pushing or pulling. There's no loss to friction or air resistance. So the work done by non-conservative forces in this example is 0. And so the energy of the system should remain constant. If this term were there, like a real system, and the ball rolled back and forth, what would it do? It would roll less and less and less and less and finally stop as the energy left through negative work due to friction. But since we're assuming it's frictionless, the total energy stays constant, the ball starts in a certain position, and even after 3 cycles, it returns to the exact same position. So there's no loss of energy. So all we have is kinetic and potential. And remember, there are 2 kinds of potential, spring and gravity, but there's no springs here. So this system starts here with potential energy and no kinetic. It loses the maximum amount of potential energy it's going to lose at the bottom. So the kinetic energy will be maximum here. And then the kinetic energy will transform back to potential energy when it stops. And that half cycle will repeat. PE is max, KE is 0, KE is max, PE is 0, PE maximum value, the same that we started with, KE0, and in the middle it would be a combination, and the total energy remains constant, and it repeats that cycle 3 times. So with those ideas in mind, you should be able to answer all the questions in this exercise. And finally, number 4, last activity, problem 6.8. Read the description, run the simulation, and then let's highlight the important information and do the energy analysis together. Do that first, as far as you can, as much as you can, and then come back and listen to what I have to say. All right, mass of the box, that will probably be important. The angle of the ramp, we may need that. Constant speed. Okay, so that means no change in kinetic energy. And maybe that's it. Let's run the simulation. Okay, 1.3 seconds up. So we want to get some information. We want to know how far the hand pushed it, right? Because we know that work is going to be the force times the distance times the cosine of the angle. And notice for the block, not very well drawn, if we draw the free body diagram, the normal force is that way, the gravity force is straight down, the applied force is this way, and there must be, right, if it's going at a constant speed, is there friction? Actually, we don't know. There's nothing in the description. So I'm going to assume there's no friction. So that means that there'll be a net work done by the person, and using our conservation of energy equation, and since the speed is constant, there'll be no change in KE, and so the work does what? It changes the potential energy. And to get the gravitational potential energy, you need the mass, we have it, you need G, we have it, we need to get the height. And so from the initial position, we get X and Y coordinates, final and initial. And so the change in X will be this, the change in Y will be that, that'll be the height. And then the distance, right, will just be the hypotenuse of that triangle. And the care is in carefully measuring it. And since the block is cubic but tilted, and the cursor goes like this, you're going to have to be careful in estimating what the center is. So you want to look, when that cursor is in the middle of the box, you want to look that it's symmetrically at the center, and it's not going to line up with the corners, right, because it's not a 45-degree angle. So you do have to exercise quite a bit of care in making sure that your cursor is at the center of the box when you get those coordinates. And just to repeat, the energy analysis is, there's a constant velocity, so the kinetic energy is constant, and so this is 0. There's an applied force, a distance, and an angle, which we have. Wait a minute, actually. You're going to make a mistake, right? Notice the applied force is this way, and the displacement is the same way. So you do not use that angle in calculating the work, right? That angle is the angle of the ramp. But this cosine theta, this is an easy mistake to make, be careful, is the angle between the F and the R. And the F and the R are both along the incline. They're not along the flat surface. So it's going to be the cosine of 0 degrees, which is 1. in calculating the work. And the change in gravitational potential energy, we discussed how to do that. And so the work done by the person results in a change in potential energy, and they have to be equal. Oh, there it is, frictionless ramp. See, I missed that. Okay, so that settles it. We don't need to worry about friction. That was what I was worried about. So that's doing problems. You see, even with all the problems I've done, I missed an important piece of information that really is essential to getting the problem right and understanding it and doing the correct energy analysis. All right, I'm going to put in a table of contents, and we're done with Lab 7. So here you see the times in the video when I start these problems, if you just want to listen to or review just one problem. Okay, good luck with the lab.